Hi, cross country kids. This is section 2-1. I wrote the homework assignment at the top of the page. We are going to be out of the book for a couple sections, and then we go back to doing like worksheets for homework assignment because they have graphs on them. So we're talking about functions and continuity. Continuity means, is it continuous or not continuous? Okay, like, is there any holes or skips or jumps or breaks in the graph or anything like that? So we're talking about whether it's continuous. A lot of times this has to, this refers to whether they are dots that are not connected or dots that are connected. So this is a continuous function. This is not continuous over here. Not continuous. Okay, so those are kind of examples of what we're looking like when we see continuous. So dots that are not connected versus dots that are connected. We'll talk about a scenario of when that happens down below. Okay, on your homework assignment, I'm going to change this just ever so slightly because they start to talk about things like one-to-one and things like onto and both one-to-one and onto. And to tell you the truth, I get them mixed up, and I teach this from year to year to year, and it doesn't really matter to me whether they're one-to-one, onto, both. I don't care. So I kind of skip over this part, and we don't really focus on one-to-one and onto. The thing that I want you to remember is whether it is a function or not a function, okay? So when it says, state the domain and range, I'm right here in the example 1, state the domain and range, we're going to do that. Then determine whether each relation is a function, so a function or not a function. Remember we did that in chapter 0. And then it says, if it is a function, determine if it is one-to-one, onto, both, or neither. You can skip that part. We're not going to do that part of it, okay? So 2 things that we need to list out. We need to do domain and range, and then we need to list, is it a function, yes or no, okay? That's mainly what we're going to focus on, okay? So domain and range, we're going to list those guys out. And here's what we got. Okay, do you remember what domain referred to? The x values. Domain is the x's, the range is the y's, okay? And we do little curly Q brackets, and this is listed in what's called roster notation. If you think about a roster like a sports roster, you're just listing out all the numbers. What are the x's? And we go in order, right? Okay, so smallest x, these are my x's, x, 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 and they go in order, right? Don't they go in order? Yeah. Yeah, perfect. Okay, so starting with -6, then we list out -5, then -3, then -1, then +6. And that's all we have to do for domain. Okay? The range, I bet those aren't in order though. -9 is first, so he's there and there. -7 is next. Yeah. So we only have to list the -9 once. Good call. Yes, we don't list the repeats. So -9, -7, and then -1 and +7. Yeah? Okay? All right. So domain and range, done. Now we have to decide, is it a function or is it not a function? It is a function, Ellie says, but the 9 repeats. The y's can repeat. So the rule is that the x's cannot repeat. This is, yes, a function. I abbreviate function as FCN. So yes, it's a function. The x's don't repeat. You don't have to say that, but I'm just putting it as a note for you to remember, like, this is how I know it's a function. The x's don't repeat if it is a function. R-E-P-E-A-T. I can't spell. X's don't repeat. That's how you can remember it is a function or not a function. Okay? Good? All right, let's go to this one. This is in table format, okay? But it's just the same thing. Like, this first ordered pair is the ordered pair 2, -2. Then I have -1, -1, etc., right? Okay, so let's do domain and range. Domain and range. Okay, the domain is the x's. So my first x is what? -2, then -1, then 2. Huh. Okay, range. Those go in order, right? -2, -1, 0, 1, 2. Function or not a function? Not a function. How's come? Because 2 repeats and the -1 repeats. So it's doubly not a function, right? No way. No way. It will always be the case that if you have fewer elements in your domain than you do in your range, it will not be a function. Is that true? Yeah, because one of those would have to repeat for one of the range values. Make sense? Okay, so if you have fewer numbers in your domain than you do in your range, automatically no, right? And you can kind of see that, okay? So we have, I kind of alluded to this at the top, where we have like graph A and we have graph B. And graph A and graph B are kind of similar to each other, except in graph B you are connecting the dots, okay? And we'll talk about a scenario of why you would want to connect the dots and why you would not want to connect the dots later. But this is called a continuous function because it continues on and it is touching every single value in between any two dots. This one is called discrete. Another word for discrete is countable. Okay, discrete versus countable. We have I have an actual spot on that dot. Okay, I have a countable number of dots on that graph. How many dots do I have? There are 5 dots. Okay, versus if you think about a line is like an infinite connection of dots. Does that make sense? So I have like an infinite number of dots that live on this line. I cannot count them. They are continuing on forever, right? Okay. All right, so we talk about continuous versus discrete in my statistics class, and let's kind of give some examples over here. So we have discrete and we have continuous, and continuous is like basically like numbers that go on forever and they connect, right? Okay, so another way to think about this is like temperature, right? Like temperature would be a continuous number because on a thermometer, let's say I measure 98.6 because my thermometer only measures to the nearest 1/10 of a degree. But my actual temperature might be 98.58, right? Or my actual temperature might be 98.582 or 98.5234761.8. I don't know. Like that decimal could continue on forever, right? It's kind of like that solid line. It's touching all of the decimal places in between like 98.6 and 98.7. Does that make sense? Okay, all of those decimals. Versus discrete would be like the number of people in class, right? I can count that. That is how many people there are in a class. Does that make sense? Okay, let's do another example. Where would like your weight, which category would that go in? Is that countable? Is that discrete? Or is it continuous? Continuous. Why?
Because it can go down lower than.
Right. So maybe my I don't want to put my weight up here on the screen. Any boy in here? You're not scared to tell me your weight? How much do you weigh, Eli? 151. 151. Did you weigh yourself this morning? Do you weigh yourself all the time? No. 151. So his scale might say 151. Or maybe it says 151.5. We'll give him 151.5, right? But the likelihood of him actually weighing 151.5 on the dot is probably not true. Maybe he actually weighs 151.48573 pounds, right? Okay, we don't know that for sure. The decimal of his weight could go on forever. Does that make sense? Okay. All right, I'm going to show you a video later on, don't let me forget, on YouTube. Anybody seen the movie A Fault in Our Stars or whatever? What is that movie called? Yeah? No? Oh my gosh, we're gonna watch that here in a second. Okay, I'll show you a clip after I'm done recording. Okay, so we're gonna watch that clip and I'll show you kind of like the difference between discrete and continuous because she talks about math and the thing. All right, discrete. Give me another example of discrete. Oh. Let me do this one. Okay, what category is it discrete or continuous? The number of stars in the sky. Discrete or continuous?
Yeah, that's good.
Can you physically count the number of stars in the sky if we had enough time?
Yes.
Yes. So the number of stars in the sky is a discrete amount. Like at this very instant, now I realize that there's stars falling out of the sky, whatever, but at this very instant, I could count the number of stars in the sky if I had enough time to do so. Heaven forbid we actually have to do that, right? Okay, but at this instant, we have a finite number of stars in the sky, right? A lot of people think that it's continuous because the sky goes on forever, right? That's not what continuous means. It doesn't mean it's continuing on forever. It's talking about like decimal numbers that would continue on forever, okay? So difference between the two. All right, let's move on. We have something called the vertical line test. So if I have not dots like we did up here, like here, these were ordered pairs, right? And it's considered to be a function if the x does not repeat, right? But if we have those lines connected, like these two things, like these are a bunch of dots where the line is connecting them, this is a parabola. If I can draw vertical lines straight up and down all across that graph and it only touches at one place, then this is, yes, a function, right? Okay, versus this guy over here, these are a bunch of dots and they are connected, so this is a continuous graph. But if I look at like my vertical lines, I have one touching here and one touching here. And let's say this is the point like 1, 2 is what it looks like, and this is the point 1, -2. If I have those two numbers in my data set, you can definitely for sure see that that's not a function. Why? The x is repeating, okay? So I can do the vertical line test if I have the graph of it, and this will tell me, no, it's not a function. Not a function. Does that make sense? If I have the graph, I just do the vertical line test. If he's touching more than one spot, not a function, right? Because the x has to repeat then, right? So let's go down here. I'm going to skip where it says determine whether it's a function. 1 to 1, on to, both or neither. State whether it's discrete or continuous. So we're going to do that, okay? We're graphing this guy. Y equals 1/2 x minus 3. That's the first thing that they want us to do. Okay? They want us to do that. 1/2 x minus 3. How do we graph that thing? Yeah, same thing we've been doing. This is a linear function, right? This is linear. It's a line, right? And we start at -3 and we go up 1/2, up 1/2, or down 1, left 2, down 1, left 2, down 1, left 2. And we connect, and is it a solid line or dotted line? Solid, and do we shade? No, it's equal to, right? So it's a solid line no matter what, and there is that. And he goes on forever to the left and forever to the right, and that's what he looks like, okay? Now, doing domain and range of these guys is going to be, is going to be a little bit harder, or maybe not harder, a little bit weirder to identify, okay? So domain and range, we don't have like points like we did up here. We were graphing dots up there. Here we're graphing a straight line. So in the domain, we're looking at what the x's are doing, right? Okay, so I'm looking at this line and I'm saying, what x's is he touching? Like what x values will he touch? X's go from left to right, right? Wouldn't he touch everything if he's going left and right forever? Yeah, so what do we put for domain? You could put infinity. I put this thing down. Do you know what that means? It's a boldface R. Okay, here's how you make it. You put two lines like this, and then you make it into an R, and that means it's touching all real numbers. So any real number you can think of all the way across. Real numbers are every number, right? Decimals, really big negative numbers, all of them, okay? All the way across. All real numbers, it's touching everything, okay? Now the range is the y values. Y's values are up and down, okay? So the range, like up and down, if I'm looking at the up and down values of this guy, what will he touch and what will he not touch? Yeah, he's going up forever, right? Not as fast as he's going out, but he is going up forever. He will continue going up and up and up forever, right? He will continue going down and down and down forever, right? Okay, so he will touch everything up and down. Agreed? Up and down, he'll touch everything. So we put all real numbers, okay? So if he's a linear function, he's going out forever to the left and to the right, and he's going up and down forever to the left and to the right. So that's my domain and range. All right, then determine whether the equation is a function. Okay, so to do this, I could look at the vertical line test. If I draw a vertical line straight up and down, is he going to touch more than one spot on each place? No. So that means yes. No means yes, right? Yes, it is a function. Does that make sense? He passes the vertical line test. Okay, the x's will not repeat. And then state whether it's discrete or continuous. Is it finite or countable, or is it connecting everything? Yeah, it's continuous. It's continuous, right? So domain and range, all reals, yes, it's a function, and it is a continuous function. Make sense? Yeah. Okay, moving on. This is my last example. Nope, no, we got a couple more examples. All right, okay, we are big kids now, and they have us now, instead of doing like y equals mx plus b, right, which is what we learned in the last section. Now, instead of calling it y, they're going to call it f of x. Have you seen that before? This is called function notation, okay? And there's a benefit to calling it f of x rather than calling it y, okay? But this is really just like saying y equals mx plus b, because the m would be the 5 and the b would be the -1, okay? So it's not really changing anything, it's just calling the y something different, okay? X is the independent variable. We get to plug in anything we want to in for x. And then depending on what we plug in for x, the y will pop out something different, right? So this is depending on what we plug in for x, okay? Normally the one that the one that you're going to plug in to the inside of the equation is going to be the independent one. And then the one that pops out is the dependent one, okay? So the benefit to calling it f of x instead of y, here's my example. Given this thing, they say f of x equals 2x squared minus 8, okay? And that's kind of like saying y equals 2x squared minus 8, okay? They say we can find f of 6, okay? They want to know what f of 6 is, okay? What does that mean? Yeah, that's all you do. 6 is taking the place of x, right? It was f of x, now it's f of 6. So they basically just want you to take, and wherever you see an x in the equation, they want you to put a 6 in there instead. Does that make sense? You're replacing all of the x's with this. What happens if there's more than one x in my equation? You plug it in for every single place, right? So there's an x, okay? All right, what do you do first here? PEMDAS. Do you remember your PEMDAS? Do you take 2 times 6 and then square it, or do you square the 6 and then take it times 2? PEMDAS is parentheses exponent, so I do this part first, right? 2 times 6 squared is 36 minus 8, and 2 times 36, Eli had it, 72, and then I subtract the 8 as the final answer. 64, you betcha. That is the final answer. Does that make sense? F of 6 just means you're taking that thing that's in parentheses, whatever's in parentheses, and you're plugging it in where the x was. Does that make sense? Yeah. Okay, moving on. B, here's B. What the heck does that mean? F of 2y. 2x squared minus 8. I'm going to write this over here so I can zoom in.
Oh, we put in 2y for x.
Yeah, that's all you do. You take, and whatever's in here, doesn't matter if it's ugly, we plug it in for the x. So 2x squared minus 8, we're going to plug in 2y into that spot. Okay, what is 2y squared? So we do this part first, right? 2y squared, what does that mean? What does it mean to square something? Times itself. So this is really like saying 2y times 2y, right? This is 4y squared, okay? Does that make sense? 2y times 2y is 4y squared, so I really have this 2 out here, but then this becomes 4y squared, right? Minus 8. Are we confused at all? Okay. All right, now what? Okay, what's 2 times 4y squared? 8y squared minus 8. Okay, what's 8y squared minus 8? 8y squared minus 8. You cannot add them because this one, the only way that you could add them together is if that one had a y squared on it also. But it doesn't, right? You can only combine like terms, right? So those two things are not like terms. Do you understand that those aren't like terms? Yeah? Yeah? So you just leave it as 8y squared minus 8, right? Make sense? Kind of ish. Okay? All right, last example. And this is the one that I really like. It says the graph shows the length. Oh, no, we have 2 examples left. The graph shows the length of the Tour de France. Do you know what a Tour de France is? It's like the bicycle race that they do. In kilometers each year from 2000 to 2013. Is the relation discrete or continuous? Discrete, right? Because they can tell me the actual length for each one of the years. It is a discrete amount. It is a countable amount, right? Does the graph represent a function? How do you decide? You could look at the vertical line test, right? So I do a vertical line here, a vertical line here. Am I going to pass through any, like 2 dots at one shot? No. What would it mean if I would pass through 2 dots at one shot? That would mean we have 2 Tour de France's going on in the same year, right? That were 2 different distances. Can you have 2 of those in one year? No. So this is yes, a function, or no, not a function? Yes, a function. Does that make sense? It is a function. We only have 1 Tour de France or 1 race going on every single year, right? Okay, all right, this is my favorite example. Example 5, choose the correct model. So we're given 2 functions here, and we're trying to choose which one of them works. And they're both the same except one of them is connecting the dots and the other one is not connecting the dots. So we're talking about buying frozen yogurt. Okay, are we clear? We know what we're doing? Okay, a cup of frozen yogurt costs $2 at a yogurt shack. Okay, so we can see like from the dots, we have 1 cup of yogurt costs $2, 2 cups cost $4, 3 cups cost $6, etc., right? Okay, that really has a slope of 2, so up here they've connected the dots and they said y equals 2x, right? If you buy 0 yogurt, you're charged 0 money, right? If you buy 1 yogurt, you're charged 2 monies, right? Okay, etc., okay? All right. The cost of x cups of yogurt can be described using the continuous function y equals 2x, right? This is the equation that we have, and that's graphed here, where y is the total cost in dollars. The graph of the function is shown at the right. Part B says the graph of the discrete function is also shown at the right. So we don't have an equation for that one, but we just have the dots. Which graph is more appropriate? Why the bottom one? I heard a lot of people say the bottom one. Why? Right, you can't buy half of a thing of yogurt. You can only buy a finite countable amount of yogurt, right? I can't walk in and say, I will have 1 2/3 cups of yogurt, please. Like, that would not work, right? So this implies that I can buy any amount of yogurt on that line, right? So that will not work. So I want to buy the discrete one. The bottom, because it is discrete or countable. C-O-U-N-T-A-B-L-E. Countable. Yeah? Does that make sense? Not too bad. Anytime it says 1-to-1, onto, or both, you can skip over that. Just tell me whether it's a function or not a function. Just do the rest of the examples. Make sense? Good? All right. Bye, people watching this video.